Hello everyone, and welcome to Past Chem class. Today I will be introducing you to different functional groups in organic chemistry. Note this is not an exhaustive list, but we will start with hydrocarbons, including alkanes, alkenes, alkynes, and arenes. Next we'll move on to oxygen groups, including alcohols, ethers, and carbonyl groups such as carboxylic acids, ketones, aldehydes, and carboxylic acid derivatives. Next is nitrogen, including amines, amides, nitro groups, and nitriles. And lastly, we will go over the sulfur groups, thiols, and sulfides. Intermittently, I will have tests for you to practice what you just learned. So make sure to have a pen and paper ready and get ready to use the pause button so you can write down your answers before I display them. I will have 2 more tests at the end with massive and ridiculous molecules full of random functional groups that you can draw, circle, and label as a good test or practice quiz for you. Feel free to jump around my video using the timestamps in the description, and please subscribe and like if you find this useful. Let's get started. Firstly, we'll talk about alkanes. Now we're going to briefly go through all of these on this page, and then I'm going to go talk about their similarities and differences. So, alkanes, here's some examples for you. We have propane, we have butane. These are commonly some cooking fuels. That's what we use them for most of the time. We have octane. You'll know it as the main ingredient in gasoline. Then, moving on to alkenes, we have chloroethene, also known as vinyl chloride. It is the monomer for polyvinyl chloride, or PVC. You can see a future video on polymerization. But PVC is more than just for PVC pipes, but also vinyl flooring, car interiors, traffic cones, jackets, deli meat packages, and much, much more. We also have ethylene. This is also an alkene, and it is a component of fruit ripening. Then let's move on to alkynes. And these are a triple bond, very high energy. Okay? So each of these, alkanes, alkenes, alkynes, these are a carbon-carbon bond, as we were talking about in the last slide. Here at the top, these alkanes, these are a single bond. Next, the alkenes are a double bond. Lastly, triple bond. And they're in that order of energy as well. Alkanes are the lowest energy, alkenes higher, and alkynes are the highest energy of these three. Alkynes can be used to make anything lower than it. You can make an alkene or an alkane. Alkenes can be used to make alkanes. In your future learning of organic chemistry, we will talk about reactions and how to make different types of molecules, and you'll find that alkenes and alkynes are very much your friend to make different things. So don't forget about these. Alkanes, most of the time when we are labeling functional groups, we don't label alkanes because so much of molecules are made up of carbon-carbon single bonds. So don't let that confuse you when we're labeling functional groups later. I am not going to label every single alkane that is out there because that is just too much. And I think most of your teachers will be on that same wavelength. Let's move on to arenes. Arenes are another hydrocarbon, or something that contains hydrogens and carbons. Arenes specifically are based on a benzene ring, this first guy here. Notice how in a benzene ring, there is only one hydrogen on every carbon. And that is because each of those carbons has one double bond and one single bond. And so it just needs one hydrogen to fulfill its octet and make a total of 4 bonds. Now, benzene is what we call an aromatic, and we will discuss more about aromatics in a future video. Find all of the links to these videos when they become available in my description below. But I will talk a little bit about it here. Aromaticity is often shown as delocalized bonds. So what that means is that electrons we like to talk about the electrons spending all of their time between this carbon, and this bond spends between those ones, and these two sets of electrons spend their time between these two, when in reality, this double bond and that double bond and that double bond spend time over here and here and here as well. And so this is often represented with a delocalized circle instead. So we can draw that benzene here, toluene with a circle there, and naphthalene will have two circles. Notice that this double bond is for this entire thing. So you have 3 double bonds and 3 double bonds on this one as well. So that is your benzene. So really anything with a benzene will be an arene. Let's move on to oxygen. We will add oxygen to our carbons and hydrogens. Our first oxygen functional group is going to be alcohols. Some examples of alcohols are these. This first one on the left is isopropanol, and this is used in rubbing alcohol, hand sanitizer. The one on the right here is ethanol, which is the alcohol in beverages and gasoline additives and many medical disinfectants. In general, alcohol is a great disinfectant. Ethers are our next functional group. Let's draw those out for you. We'll come back to those later. Ethers are the next functional group, and here are some examples. To name them for you, but I'm not going to go through and list them, especially that one. Okay, so with these ethers, if we redraw this diethyl ether here and color code that one and the isopropanol, let's look at the oxygen and what they are attached to. So for the ethers, you can see that here the oxygen is attached to both a carbon on the right and a carbon on the left. These carbons can also be represented by an R, but ethers must be attached to a carbon on both sides. For the alcohol, it has to be attached to a hydrogen on one side and a carbon on the other. That is the definition of an alcohol. And you'll see something similar in the future with carboxylic acids. Don't get them mixed up, but we'll go over that when we get there. So alcohol, oxygen is attached to a hydrogen and a carbon, ether attached to 2 carbons. Let's move on. So I mentioned carboxylic acids. Carbonyls are part of these, but specifically carbonyl is a part of a lot of groups. Now, a carbonyl is a carbon double bonded to an oxygen. These are part of many functional groups, and it depends on what this carbon is attached to. It's always attached to 2 different things, one thing on each side, always 2 things, never more, never less. And that thing on either side could be a hydrogen or anything else. So this carbon in the middle here is called the carbonyl carbon. You'll want to be able to identify it, and again, identify what it's attached to, know what this molecule not only is called, but how it will function when you do reactions. And let's just talk about the oxygen real quick here. I did draw these dots on here. Those are called lone pairs, if you aren't familiar with them yet. Sometimes they are drawn, sometimes they aren't. Whether or not they are drawn, they are there. I don't put them on every single molecule I have, but know that they are there. And your teacher may or may not care if you draw them. Know your teacher's preferences. Some professors want you to have them all the time or they will dock you points. So know those preferences and follow accordingly. Also, one last note, carbonyls may have an oxygen up like this, or they may be down like that. But regardless, it's a carbonyl group, and I want you to recognize it the second that you see it and start labeling what kind of functional group it is. Okay. First things first, we will talk about ketones. Ketones have a carbonyl group that look like these. Okay, here's some examples. We will start with acetone here on the top left, and I'm going to redraw it out here for you to take a closer look. So I am going to isolate the carbonyl, draw a box around it, and we'll isolate the carbonyl in each of the others as well. Okay, there's that one, all of those. Okay, I want you to start doing this in your mind, even out on a piece of paper. Go, okay, here's the carbonyl group. Next, we will isolate the carbonyl carbon. Here it is on each of these. Okay, now we will point out what the carbonyl carbon is attached to. So on one side, we have a carbon. On the other side, it is attached to a carbon. That is what defines a ketone. It has to be attached to a carbon on each side. So again, these carbon chains can be described as an R. So I could describe it as R1 and R2 with double bonded oxygen, okay? But these R groups can represent a long carbon chain. It could just be one carbon, but it can't be a hydrogen, okay? It has to be a certain length of carbon chain. Next is aldehydes. An example is formaldehyde, which is known for the preservation of animals or cadavers for dissection. You may have done that in science class. Cinnamaldehyde here, it gives cinnamon its traditional smell. And an aldehyde will always be at the end of a chain attached to at least one hydrogen. This hydrogen may or may not be written. So here are a few orientations that can be drawn in. So I'm going to pick cinnamaldehyde here. Notice that the oxygen is pointed up, the hydrogen is down. For this next one, same molecule, we've got the oxygen pointed down and the hydrogen is not there. The oxygen took its place. And then lastly here is another way it can be drawn. The oxygen is still pointed up, but the hydrogen is not drawn here. So here's some pretty common ways. I want you to be able to recognize all of them. They're all at the end of a chain. They're all the same thing. They're all an aldehyde. Now, an aldehyde can be attached to two hydrogens, as it is here, but there's only one of it. If it's attached to two hydrogens, it has to be formaldehyde because you can't continue on the chain here. So every other time we have an aldehyde, it is attached to one hydrogen and one carbon. All other aldehydes, this is the only one attached to two hydrogens. Again, we're going to box all of our carbonyls. There's that one and the rest of them. And lastly, where is our carbonyl carbon on the cinnamaldehyde? It is that one right there, okay? Next, we're going to talk about carboxylic acids. And note the word acid. Acid is what makes things sour, so you may recognize some of these. Acetic acid here is the molecule that makes vinegar sour. Citric acid is the distinct sour in lemons and limes, but it's also in many other fruits and veggies as well. And here is butyric acid. We're going to look closer into this guy here. So if we box the carbonyl, there it is, and we look on one side, we have a carbon, and on the other side is an OH group. Now this OH group is not an alcohol specifically because it is attached to a carbonyl carbon. Any other time you see an OH group, it's an alcohol. At this moment, because it's attached to a carbonyl, it is a carboxylic acid, okay? So the difference between each of these three, let's go over it again. Ketones have a carbon on each side. A aldehyde have a carbon on one side and a hydrogen on the other. And a carboxylic acid has a carbon on one side and a hydroxide or an OH group on the other. Okay, so coming up here is our review. It's a little pop quiz. Don't be too worried though, because there is no grade. That is the best part about practice tests. Okay, So if you haven't already gotten out a piece of paper, get one out. You'll want to practice these. So draw out each of these molecules, and then you're going to want to box the carbonyl, then you will circle the carbonyl carbon, and then you will label the functional group. Okay? Don't forget to pause the video because I am about to give you the answers, okay? So pause. Okay, so here are the answers. Here are the carbonyls. Here are the carbonyl carbons. And then I'm going to throw them into each of the following groups, okay? Go ahead and pause it if you want to check your answers. Next are the carboxylic acid derivatives. These will make more sense when we get into reactions. However, suffice it to say that the OH group of the carboxylic acid that's up here, this OH group, will be effectively replaced. Now, starting with our acyl halides, keep an eye on the OH group and what it turns into. And remember that halide or halogens are the elements in group 7. So fluorine, chlorine, bromine, iodine. So here's some examples. Our acid anhydrides, these are two identical carboxylic acids that react with each other. So you'll notice that they are symmetrical. Next are esters, which form when a carboxylic acid reacts with an alcohol. And lastly are amides when it reacts with an amine. Note in the esters, the methyl salicylate, that is wintergreen, which is a topical NSAID, just for your GWiz collection. Next, I will box all the carbonyls like I'm going to here the carboxylic acid. So there are all our carbonyls. Next, we will look at the hydroxide here and what it turned into in each of the groups. So firstly, with these acyl halides, remember that halides are these guys here. The OH becomes a halide. So we're going to draw a generic statement for these. You have a carbon double bonded to an oxygen, so your carbonyl attached to an X, which is representative of a halide in organic chemistry. And then don't forget that we're still going to have a carbon over here on the other side. I just don't mention that because that is part of the carboxylic acid. It has to be attached to a carbon over there. Okay, next we're going to talk about the acid anhydrides. Remember, as I said earlier, it's two carboxylic acids that are identical that reacted with each other. So imagine two carboxylic acids like this that face each other, and we get this. The two OH groups combine into just one oxygen, and they become this, okay? So this would have been your carboxylic acid before. You have two of them. They're attached there in the middle. These can be generically represented with the carbonyl on each side connected with an oxygen in the middle. Next, if we talk about our esters, you'll see they have the oxygen here. That's what the hydroxide turned into, is this oxygen connected to a carbon chain of some kind. So if we represent that generically here, we have a carbonyl, then oxygen, then a carbon, which also can be represented by an R, as we talked about earlier. Next, we have amides. We haven't talked about nitrogens yet, but we will in this next section. So these, that OH group is replaced with a nitrogen. And that can be a nitrogen without any other carbons attached. It can have a carbon chain. It can even loop around and form a ring. Either way, no matter what way you do it, if you have your carbonyl attached to a nitrogen on one side and a carbon on the other, like I said earlier with this acyl halides, I haven't mentioned repeatedly, but each of these, the other thing the carbon has to be attached to is another carbon. For each of these, a carbon here and a carbon there. But the carbonyl has to be attached to a nitrogen on one side. So like I said, we're going to move on now to nitrogen groups. I will start with the amines. They are subclassed into primary, which has nitrogen attached to one carbon chain, has to be, remember, a minimum of one carbon, and two other hydrogens. Then we have secondary, which has two carbon chains and only one hydrogen. Next is tertiary, which has three carbon chains and no hydrogen. And then lastly, if you remember from my last video, nitrogen likes to make 3 bonds, but it technically can make 4, but its formal charge will be +1. So this quaternary cation will have 4 carbon chains attached to it, but it will have a formal charge of +1. We'll talk about formal charges in another video. But this fourth carbon chain, as you see here, will take the place of nitrogen's lone pair of electrons, which I have not drawn in any of these so far. If I wanted to, we could draw in, we could draw in lone pairs for all of these nitrogens. Remember, it is your teacher's preference if you need to draw them all the time. I don't draw them all the time, but I do every once in a while. But this nitrogen here in the quaternary cation does not have any lone pairs. This fourth carbon chain has replaced those. And so it does have a formal charge of +1. But this quaternary cation will be ionically bound to an anion, and it will create a quaternary amine salt. Sorry, that's hard to say fast. Moving on here, we will show some examples of each of these. So here's the primary amine. You can see that this nitrogen is got 2 hydrogens attached to 1 carbon. Next we have this guy. Nitrogen has 2 carbons branching off of it. This one has 3. And lastly, we have 4 here. Next, we're going to summarize these up here. Okay, we're going to, we already talked about the amides, so quick review. Remember, it's the carbonyl attached to a nitrogen. That's an amide. These are amines, where it's just the nitrogen, no carbonyl group. A nitrile is also known as a cyanide. These are characterized by a nitrogen triple bonded to a carbon, single bonded to another carbon, as you see here. And the reason this carbon has to be single bonded to another carbon is carbons can only have 4 bonds, and if it's triple bonded here, it only has 1 bond left here. So name and some more example. And then again, here is our representation. The carbon triple bonded to a nitrogen, and the carbon is also single bonded to an R group, which here has to be a minimum of a hydrogen. It can be a carbon chain, which it usually would be, but it could also be a hydrogen, making it hydrogen cyanide, which is a very poisonous gas. Nitro compounds involve an NO2 directly bonded to a benzene ring, like this one here. When drawn out, it looks like this. Now, you will notice in some textbooks and other things you'll see in the future about resonance, this oxygen may have a double bond or it may be over here. And we've talked about it switching back and forth very rapidly to the point where it actually, the electrons spend equal time in both lending to it being more of a 1.5 bond rather than a single bond and a double bond. And this is represented with a dotted arch instead of this second line here. So you'll have one line, another line, and then this dotted arch here. So that would be your showing that the electrons spend time, just like we had the circle earlier for our benzene ring. You will learn later on that this is electron withdrawing group, meaning the oxygens are pulling electron density towards them away from the ring. Or in simpler terms, electrons, which usually favor being in the benzene aromatic ring here, are drawn away to spend a little bit more time with the nitrogens and oxygens over here, allowing for reaction to happen on the other side of the ring, as we will talk about in a later time. As we did before, we have a little quiz. So if you grab out your piece of paper, you can draw out these 9 structures and then label them with the appropriate functional group, including primary, secondary, etc. for the amines. And don't forget to pause because I'm going to put up the answer in 3, 2, 1. All right, moving on here. Next, we will talk about sulfur functional groups. If you notice here, sulfur is in the same group as oxygen, this group 6. What this means is not only do they want to make the same amount of bonds to fill their octet, they also make some similar and comparable functional groups to oxygen. Alcohols are like thiols, and ethers are like sulfides. For an alcohol, if you remember, an OH group attaches to a carbon chain. This, although we didn't differentiate before, is a primary alcohol, where the oxygen is attached to a carbon, which is attached to only one other carbon. If we make a comparable thiol, we have a primary thiol here. We just replace the oxygen with a sulfur. If we have a secondary alcohol, we have an oxygen attached to a carbon attached to 2 other carbons here. That makes it secondary. If we had a third carbon here instead of a hydrogen, that would be a tertiary alcohol. Now, an oxygen with a hydrogen already attached to it can only attach to one other thing. That's why it's not attached to multiple carbons here. That's not possible. It has to be this carbon that's attached to other carbons, okay? So a comparable thiol for this secondary thiol, we just replace with sulfur. Here is our secondary thiol. So here is our representation here. OH attached to an R group, SH attached to an R group. Next, we have ethers, okay? We draw this out here, the oxygen is attached to a carbon, also another carbon on the other side. Sulfides work the same way, sulfur attached to a carbon on each side. Again, we can draw it out this way, our group on one side, our group on the other. The only difference is an oxygen or a sulfur in the middle. Now let's do another quiz. So please draw and label all the sulfur functional groups. If you've got another piece of paper, this is a good practice for you. Don't forget to pause the video as the answers are soon to follow here. 3, 2, 1. All right, next we are going to do a larger test. This quiz is going to go over the material from all of the slides. So what you're going to do is you will draw this molecule and then you will circle each of the functional groups and label it with the appropriate name. So draw it all out, circle each functional group that you see, and label it. Don't forget to pause the video. A quick plug-in, if you are finding this helpful, please like and subscribe to give back to a free tutor. If you like how I teach, I do live tutoring as well. Email me at passchemclass@gmail.com and or come back for more videos. Okay, so first I will circle everything. Make sure you have all of these, so pause here, make sure everything is circled. And here are the names. All right, I have one more of these. Again, draw the molecule, circle the groups, and then label them. If you pause here, you can do that. All right, here are your circles. And here are the names. All right, thank you everyone. I hope you enjoyed this video, and I will see you for my next video.